That's our sun. And that's little Earth to the right of it. And the sun just ate Earth. Don't worry though, that's not gonna happen to us. Yet. What I just showed there was the sun essentially eating Earth. But that isn't exactly what happens. The sun was simply expanding as it was becoming a red giant. And Earth was just a victim in the process. That is one of many evolutionary paths stars can take, and that path is what our sun will eventually go through. But the sun doesn't start there. Like how you are who you are now, the sun was at one point you can call a baby, a protostar. Protostars form from nebulae, which is a fancy word for dust clouds in space. If I were to explain the whole process, it would take a while, so I'll keep it short. Inside the molecular cloud, dense clumps of gas come together by gravity and get bigger until they become cloud fragments. These cloud fragments eventually become protostars, and this whole process takes about 10 million years. Eventually, the protostar accumulates enough mass that it has enough gravity to start fusing atoms, which is what a star does. At this point, stars are fusing hydrogen atoms into helium atoms in their core for a long time. How long stars are fusing hydrogen atoms depends on their mass. Larger stars fuse hydrogen and other atoms faster, so they have shorter lifetimes. Smaller stars fuse hydrogen and other atoms slower, so they have longer lifetimes. Intermediate mass stars, the size of our sun, 0 and 8 to 1 and 4 solar masses, will last about 10 billion years in their hydrogen fusing phase. The sun is about 4 and 6 billion years old, halfway through its hydrogen burning phase. However, when all the hydrogen has been fused into helium, the star will expand into a red giant. And the star will be fusing helium atoms into carbon atoms. The star will spend a few 100 million years to a billion years fusing these atoms. After the star fuses all the helium atoms into carbon atoms, it sheds its outer layers into a planetary nebula. What's left of the once-was red giant is now a white dwarf, the core of the star. The star will have lost half its mass but be roughly the size of Earth. Eventually, after hundreds of billions of years, the star will cool into a black dwarf. However, even the oldest white dwarfs have yet enough time to cool, so black dwarfs are completely theoretical. This evolutionary path of stars is available to most stars that are about 0 and 8 to 8 times the mass of our sun. High-mass stars follow a slightly different evolutionary path. It still starts with a protostar from a molecular cloud to a star. But this time, the star has accumulated more mass, about 8 to 20 solar masses, and has stronger gravity, meaning it fuses hydrogen into helium faster for about 100 million years, less than 1% of how long the sun will fuse hydrogen. Meaning it will run out of hydrogen faster and become a red giant faster, but instead it's called a red supergiant. The only difference between a red giant and a red supergiant is a red supergiant is super. Not really, red supergiants are just a lot larger than red giants. In this phase, the star is still fusing helium to carbon, but this time it does not stop there, fusing atoms into heavier elements like neon, sulfur, and silicon. The red supergiant will then be fusing silicon atoms into iron atoms. In some cases, this could last a day. After that, iron can no longer fuse into heavier elements, so there is no longer anything pushing against the star's gravity. The star collapses in just a second and explodes in a supernova explosion. What happens next once again depends on the mass of the star. For stars 8 to 20 solar masses, they collapse into a neutron star. These stars are almost entirely comprised of neutrons and are extremely dense. Stars with over 20 solar masses collapse into a black hole. Black holes have such strong gravity that not even light can escape it. Protostars can also turn into a red dwarf. These behave like the typical intermediate mass star fusing hydrogen in its core, but are incredibly small, being 0 and 0.8 to 0 and 6 solar masses. These stars are so small that they have much weaker gravity and fuse atoms much slower, meaning they can last a long time. These stars can live to trillions of years, and when all their star buddies die, they'll be the last light objects in the universe. Okay, so it should be taken note that just about everything in this video is not entirely to scale, like neutron stars are actually really small. Also, solar basically means sun, so when I say solar mass, I mean mass of the sun. And a mistake I noticed but was too late to reanimate was that when those two heliums with one neutron fuse into your typical helium, 2 protons are released. And also my voice changes pitch a lot. and is a little bit hard to hear, so sorry about that.